Thank you very much. Thanks a lot for the very kind introduction. And well, thank you very much for the invitation. It's really a pleasure and an honor to be giving this Gauss lecture. So since, well, obviously the audience here is quite mixed. So there are, professional mathematicians in the audience, but there are also high school students in the audience. And so I thought I would start by asking a very simple question, which is, what is actually mathematics? So, in school, a lot of what you do when you do mathematics in school, when you learn mathematics, is you actually learn how to compute. Right? So in the very beginning, you learn how to multiply numbers, but then maybe you do a bit more complicated computations. You learn how to solve equations, or maybe how to differentiate functions, or things like that. But I would say, in a way, computing is to mathematics maybe a little bit like what spelling or grammar is to writing, right? Obviously you need to know grammar in order to be able to write a book, but it's not really the essential thing, right? So if you want to be able to write a book, you need to actually come up with an original story. You want to have a very original plot. And then, of course, you need to put it to paper. You need to be able to write it. But the important part of the story is the plot. It's the story, right? It's not actually just the writing, even though, of course, if you write well, you can use very beautiful language, and that's an important part of the book as well. Right? And it's a bit similarly with mathematics and computing. So actually, so what you see here on the slides are computers. Okay? So until the 60s or 70s, being a computer was a job, right? I mean, now, of course, you have electronic computers, and even, all of you have a very powerful computer with you in your pocket, which you call a phone, but it's really a computer. Until the 60s, computers, being a computer was basically a job, but it was not a job for mathematicians, right? It was sort of a medium-skilled job. Anyone could do it. You could train for the job. It would be like a 1-month training or something like this, and then you could be a computer. Right? So anybody can learn how to compute pretty quickly, and you can do it as a job. Well, now, of course, that job doesn't exist anymore. But you could. And so if mathematics isn't computing, what is it? I mean, to some extent, it's really just exploring the world of ideas. Okay, so it's just like in the allegory of the cavern of Plato, which probably most of you have seen that story. The idea being that we are a little bit like people in the cavern here, who only see shadows of the world of ideas out there, and who try to kind of make sense of this world of ideas with only this sort of partial information that we see, with these shadows that we see on the walls of the cavern. And in some sense, mathematics is really the exploration of this outside world, right? This world of ideas. And it's, you try to, in some sense, build concepts and say, meaningful sentences about them, about objects that really have no logical contradictions, if you want. And you try to be as precise, you try to be absolutely precise in what you actually mean, right? So a big part of mathematics is to be able to actually define things in a completely unambiguous way so that you really know what you're talking about, right? So in that sense, being a mathematician is a little bit like the opposite of being a politician, right? So, if you're a politician, then being imprecise is a feature, right? Because you want to say something which means different things to different people, right? Because if you want to get elected, you want as many people as possible to kind of agree with you, but people don't agree with each other, and so you have to say things which mean different things to different people, and so then everybody can agree with you, even if they don't agree with each other, right? So as mathematicians, you do precisely the opposite of that, okay? So you try to be extremely precise so that when you say something, you know exactly what you're saying, and the person you're talking to knows exactly what you're saying, right? And so if you want, all mathematicians in the world would always sort of agree of what, the meaning of your sentence is. And so that's basically the only way in which you can, come up with really true statements, right? I mean, nowadays, the truth has sort of become almost like an old-fashioned thing, right? I mean, if you look at what happens in politics nowadays, basically people have become completely cynical and sort of nihilistic in a way, and saying, well, actually, you can just never know anything about truth, and truth doesn't exist anymore. So, I mean, mathematics is maybe, one of the rare places where you really have sort of absolute truth, or really truth that is sort of as absolute as logic actually permits it, right? So that's in some sense, mathematics in general. Now, this is very abstract, of course, right? It's sort of, you build or you describe just sort of logical concepts. But of course, mathematics has links to the real world, right? I mean, the reason why mathematics has been so successful is partly because of its applications to kind of describing the real world. And there are different ways in which it's linked. So one way is physics, right? So the job of physicists, in a way, is basically to link mathematics to the real world, right? To come up with mathematical models that provide meaningful statements about, real world phenomena. Then there are people doing modeling. So in some sense, physics and modeling, it's almost the same thing, except that you can think of physics as going sort of bottom up and modeling as going kind of top down, in the sense that physicists try to have some kind of fundamental understanding of, basic processes in the world. So you try to come up with very fundamental principles like conservation of energy and conservation of mass or things like this. And then you sort of build the laws of physics on top of that. Whereas if you do modeling, maybe you might be informed by the laws of physics, but you would take more of a top-down approach where you would say, well, maybe that phenomenon is sort of too complicated to actually figure out the laws that regulate it, so from the bottom up. And so you just try to come up with some heuristics in order to kind of describe it. But still, you build a mathematical model in order to describe some phenomenon from reality. And then there's maybe a third way in which it links, which is somewhat special, which is somehow there's a link between mathematics and computers. In a way, a computer is almost like a computer in the sense of, your phone. It's really like some sort of a physical embodiment of mathematics, right? So what goes on in some sense inside of a phone, or when you program a phone, it's essentially mathematics. And it's as close as you can get in some sense to a, like manifestation of pure mathematics in the real world in a way. Now, personally, I'm probabilist, so my area of mathematics is probability theory. So most of this lecture is going to be about that. And so let's start. I mean, there's one thing which is kind of interesting about probability theory, which is that, we all have some sort of intuitive idea of what a probability is. But, people can still actually argue about it. If you think about it, it's not completely clear. And maybe one reason for this confusion comes from the fact that to some extent, there are really two different real-world phenomena that we both call probability, and that they are not quite the same thing. And the first one, if you want, is a more subjective type of probability, which is kind of related to your beliefs, right? So to be more precise, take the following situation, for example. So, next year there's going to be an election in the United States, and you can ask yourself whether Trump is going to be elected president. Right? And now take the statement, what is the probability that he's going to be elected? Now, say you think the probability is, 40%. Now, what does this 40% actually mean? So let's say I want to sell you a piece of paper, okay? And the piece of paper, if you own that piece of paper, then the day after the election, if Trump wins, you get €100. Okay? If he loses, you get nothing. And then the piece of paper is worthless after that. Okay? The question is, how much are you willing to pay for that piece of paper? Okay? And the claim is that if you're willing to pay, what's the maximum amount you're willing to pay, right? So if you're willing to pay 99 euro for it, that means that you're really pretty certain that he's going to win, right? Because otherwise you're losing money. Whereas if you're only willing to pay €1 for it, it basically means you're not willing to buy it, and so it means you're basically certain that he's going to lose, right? If you're willing to pay €50, that means that you think he has a 50% chance of winning. If you're willing to pay €70, it means you think he has a 70% chance of winning, and so on. Okay, so that's a kind of subjective, if you want, definition of probability, and that's for events that are kind of one-off, because that election is going to happen 1 year from now, and that's it. It's not going to be repeated, right? It happens once, and that's it. There's another type of probability that appears in situations where you have an experiment which is repeatable, right? So it's an experiment where you don't know, just like in the election, you don't know the outcome. You cannot possibly predict the outcome. Like, nobody has the information required to predict the outcome. Maybe even in principle it wouldn't be predictable. But you can repeat the experiment. And then you can ask yourself, how often do the different outcomes occur? Okay? And so that's, if you want, a more sort of objective or a posteriori definition of a probability, where, like, for example, you roll a die, you can roll the die 1,000 times. It's the same experiment, even if it's not exactly the same, in the sense that every time you roll it, you're going to roll it a tiny little bit differently, right? But for all practical purposes, it's the same experiment. So you can repeat it as often as you want. And so then saying that the probability that you roll a 6 is 1/6 just means that, if you roll it 1,000,000 times, about 1/6 of the time you're going to get a 6, right? That's, if you want, for the mathematicians in the audience. In a way, it's sort of the difference between a Bayesian and a frequentist perspective, which statisticians spend a lot of time arguing about. And the claim is that it's basically two different types of setups, and both of them arise in the real world. And it so happens that both of them are described by what we call probability theory, but they're actually just fundamentally slightly different things. But then once you have these probabilities, right, then we have various rules to work with them, right? So we know that, for example, if you have, if there are different outcomes, say A and B, then the probability that one or the other happens is the sum of the probabilities. If they're mutually exclusive, like the probability that you roll a 6 is 1/6, the probability that you roll a 1 is also 1/6, and the probability that you roll a 1 or a 6 is 1/3, right? And so on, and then you multiply them. So in some sense, and corresponds to multiplying if they're independent, etc. So we have various rules to work with these probabilities. But at some point you still have to assign them, right? So you have rules for working with these probabilities once you have them for certain events. But you need to come up with these probabilities of somehow the simple events to start with. And there are essentially two guiding principles for doing that. And the first one we've already seen in the example of the rolling of the die, which is symmetry. Right? So that's the situation where you do an experiment, there are different outcomes, and the different outcomes, you are able to distinguish between them, but as far as the mechanism of the experiment is concerned, it doesn't make any difference. Right? So it's like when you roll a die, you can see whether it comes up 1 or 2 or 3 and so on, right? But if the die is completely symmetric, as far as the rolling is concerned, it doesn't make any difference, whether it's in one position or in the other position. Right? Same for tossing a coin. Right? Like, you can see whether it comes up head or tails, but as far as the coin toss is concerned, it doesn't make any difference at all. Right? And so in this case, well, if you're in a situation like this, where you have different outcomes that you are able to distinguish, but the mechanism that produces them cannot distinguish between them, then it's natural to assign equal probabilities to all of these outcomes. Right? Like, you roll a die, there are 6 possible outcomes, they're completely indistinguishable, so each of them has probability 1/6. Right? Coin toss, each of them has probability 1/2. So there's only 2 outcomes. Well, unless you're really, really lucky and the coin just, And then there's another principle, which is more subtle, and that's something which is much less intuitive, which is something called universality. And actually, it's quite fitting that, Gauss's name is attached to this, actually, which we're going to see in a second, at least to part of this. So universality is this fact that actually in situations where, you have some random outcome that is actually, it arises from somehow many, many different kind of random events that combine in order to produce some outcome, then very often in some kind of limit, the probability distribution of the outcome doesn't really depend very much on the details of the probabilities that you assign to all of the little random events that kind of combine to produce the outcome. So one way in which this arises is what's called the Gaussian distribution, right, which is named after Gauss, the same Gauss as the Gauss from the Gauss lectures. And so what's the Gaussian distribution? Well, for example, one thing you can do is imagine you take a coin and you toss it 100 times, and you count how many times it comes up head. Right? So if you toss a coin 100 times, and you look at how many times it comes up head, well, on average, it would come up 50 times, but typically it's not exactly 50 times, right? I mean, sometimes it's 47, sometimes it's 51, whatever. And so maybe I do that experiment itself 1,000 times, right? And then I do a histogram. I look at, how many times do I get 50 heads, how many times do I get 51, 49, and so on. And so here I've done that experiment. So, I mean, obviously I didn't toss a coin 100,000 times, but I just asked the computer to do it. And you get a histogram like this. So in this particular case, you see, for example, the 50 is in the middle here. I actually got like 49 heads a little bit more often than 50, right? And then 51, again, slightly more often than 50. But it sort of roughly distributes on some kind of curve like this. So if you do it 10,000 times or 100,000 times, right, so if it gets closer and closer to that curve, and that curve is called the Gaussian distribution. And the beauty of it is that it's the same curve that shows up if you do that sort of statistics, for pretty much any distribution. So here, I just tossed a coin and counted how many times it came up heads. But I could have, for example, rolled a die and counted how many times I get a 6, which is not quite the same thing, right? Because the probability of getting a 6 is only 1/6, and the probability of getting head is 1/2. But, if you do the same kind of experiment, the curve that you're going to get is going to be exactly the same. It's going to be shifted a little bit or translated or sort of scaled around, but it's going to be exactly the same curve. And in many, many situations, it's basically always in situation where you have like many small random quantities that are more or less independent and that you add up in order to produce a large random quantity. right? So basically in every situation like that, this Gaussian distribution shows up. And so then, when you're in a situation like this, you know that you get something Gaussian, and you don't actually really need to know the details of what's the distributions of all the little things that add up to something big, okay? And so that's a really important principle, right? Because it tells us that we can basically make predictions on random systems even if you don't know all the details of the mechanism of how these systems work. Now, these two principles, they appear, at least the first principle seemed pretty clear, right? I mean, the second principle is a bit less clear because also my explanation was a bit sort of wishy-washy. The first one seems very clear, right? But even the first one, you have to be a bit careful. So for example, take the following situation. So say I have two envelopes, okay? And the only information I give you, so each of them has a check in it. And the only information I give you is that one of the checks has twice as much money as the other one. Okay? And then you open an envelope, and you see what's written on the check. Okay? You're allowed to look at it. And then I give you a choice. So either you keep the money, or you can change your mind. Okay? So you can take the other envelope if you want, which has either twice as much or half as much. Of course, if you change your mind, then you're not allowed to change back if it was, if it's the one with the smaller amount. Right? And so the question is, what should you do? Well, if you change your mind, how much do you get on average? So say in the first envelope, you have X euros. So then in the other envelope, well, there's, half chance that there's twice as much and half chance that there's half as much, right? So on average, it's a half chance of half as much plus a half chance of twice as much, which is 5/4 of the value. So you should change your mind, right? Because you get, on average, you get 5/4 of what you get if you don't change your mind. But it works for every value of X, right? So you didn't even need to open the envelope to know that. So you should have just chosen the other one before you even open it, right? Which doesn't make any sense. So what's the problem here? The problem is that, it sounds like one of these situations that are symmetric, but they're actually not, right? If you really think, so for example, replace the 2 by 1,000, right? So say the other envelope has either 1,000 times as much or 1/1,000 times as much. Then it's even clearer that you should change, right? Because now it's a half chance of getting 1,000 times more and a half chance of getting basically nothing. So you should always change because you get basically 500 times more, right? But now, let's think sort of real world situation. You open the envelope, you see 10,000 euros in it. What are you actually going to do, right? You're obviously not going to switch, right? Because I would be really crazy giving you 10 million euro. I don't have 10 million euro for starters, right? So, so you make it sound, so the thing is, right, you make it sound sort of like a cute little math problem where you have this X and it doesn't mean anything. But there's really a difference between 1,000 euros and €1 million, right? So it's actually not symmetric at all, the situation. And so, this is sort of just a cute little problem, but there is this, there's a trap one can fall into, which is to take some real world situation and turn it into a little cute little mathematical problem, and then you do the calculation, you get some outcome, and then you say, oh yeah, okay, so this is what the outcome in the real world is supposed to be. And you don't realize that you've actually dramatically oversimplified what's going on. And there are situations where this can have actually dramatic consequences. So there's a case that happened, I don't know when it was, maybe 10, 15 years ago, or something like that, in the UK. There was a lady called Sally Clark, and she had a child. And when it was, I don't know, just a few months old, sometimes, babies actually die for unexplained reasons, right? So it happens very rarely, but it can happen. It's called sudden infant death syndrome. And, well, that happened in that case. And 2 years later, she had another child, and the same thing happened again. Okay? And so then some people got suspicious because they thought, well, you know, what's the chance that actually this will happen twice to the same family? So maybe she actually murdered her children. And so she was accused of murdering her children just on the basis that it would be extremely unlikely that this happens, you know, by itself. And so there was a trial, and there was an expert witness who, you know, then testified for the prosecution and said, well, you know, in a family of this and that social background, the probability of having sudden infant death syndrome for a child is about 1 in 20,000. And so the probability of having 2 children in the same family dying of it, well, it's 1 in 20,000 times 1 in 20,000, so it's 1 in 400 million. And so it's so unlikely that this couldn't possibly happen, and so she must have killed the children, right? And she actually got convicted, and she spent, I don't know, 7 or 8 years in jail before the conviction was overturned. And of course it was overturned because, you know, the verdict was completely ridiculous. There are 2 mistakes here, right? So the first mistake is to think that 1 in 400 million is really small. I mean, 1 in 400 million is really small, but there are 20 million families in the UK. There are billions of families in the world, right? So the chance that it actually happens to some family is very high. Right? It's just like if you play the lottery, the chance that you win the lottery is very low. Right? The chance that someone wins the lottery, well, you know, it happens every week. Right? So, I mean, here it's of course the opposite of winning the lottery, but and the other mistake was to just multiply the probabilities, because you can do that for independent things, but there's no evidence that this is something independent. Right? I mean, it may very well have some genetic component. As far as I know, it's not completely clear, but you know, a priori, you can certainly imagine that there might be a genetic component to it, and then that means that if one child dies of sudden infant death syndrome, well, it may be because of some genetic reason, and if that's the reason, there are good chances that the other child will have the same condition and would die for the same reason, basically, right? And so you cannot just naively multiply the probabilities. So now let me come back to this other question, so this principle of universality, right? So I mentioned the Gaussian distribution, but now I want to mention also maybe a more sophisticated type of universality that shows up, which is in some sense quite similar to this Gaussian distribution. And so that's related, that's what's called Brownian motion. And so Brownian motion, so it's named after Robert Brown. So he was a British botanist in the 1800s. And what he did is he was actually looking at pollen particles under a microscope. Right? So he had some sort of little pollen particles under his microscope, and what he would, like here you see these particles, and what he would see is actually something like this. Right? So you look at these particles under the microscope, and you see them moving like this. Right? They make this sort of little jittery motion, and so he was trying to understand why they do that. So of course he was very careful to kind of make sure that, you know, the water itself was not moving anymore, so that it wasn't just because they were kind of being transported around. In the beginning, he thought, you know, maybe these are actually alive, that they're, you know, like sort of tiny little animals that move around. But then he made sure that to rule that out, so he made sure that, you know, there would be no light, no nutrition for weeks or something, and then even after weeks, it was still doing the same thing. So it was pretty clear to him that they weren't alive. And so there was this question of, you know, why do you have this Brownian motion? Where does this come from? And it's actually a question, it's interesting because that was sort of in Victorian England, where this question did actually sort of catch the imagination of the general public. So it was, like a topic of conversation for high society. Was this question of, can you actually understand of why there is this Brownian motion? Of course, the explanation that people came up with and sort of a quantitative version of this explanation was then actually provided by Einstein and Smoluchowski. So it's one of Einstein's famous 1905 papers where, it's in two parts. So there's the physical reason, of course, which we kind of all know now, is that, water is made of molecules, and the molecules of water, they really behave a little bit like little billiard balls. So they kind of just move in straight lines. And if you want the temperature of the water, it's kind of like the speed of these billiard balls. Now, they all move in all directions in completely disordinated way. So now, your pollen particle, it's a very small pollen particle, but it's huge compared to a molecule of water, right? So you have this huge pollen particle that gets bombarded by molecules of water from all sides. Every time there's a molecule of water that bounces off it, it gives it a little push, and it pushes it in one direction. But, a molecule of water is so small that, you basically don't see the effect. But there's billions and billions and billions of molecules of water that push it all the time, and the cumulative effect actually does make it move, and that's what you see under the microscope, right? And Einstein and Smoluchowski, they actually made that also quantitative, and they were able to predict kind of by how much it's supposed to move. And mathematically, the description they gave was in terms of what's called the heat equation. So it's basically saying, what they did predict is how does the probability that the particle finds itself at a given location evolve over time, right? Like imagine you see the particle at some point, and then you close your eyes, it sort of moves around randomly, and then you try to predict, like 1 second later, where it's going to be. Since it moves randomly, you can't tell for sure. The only thing you can give is sort of maybe some probability distribution. And it turns out that probability distribution is actually, again, the Gaussian distribution. But on the other hand, it's also related to the evolution of heat in a solid body, right? So imagine that you take, instead of looking at how probabilities evolve, you look at how heat evolves. So you take, for example, a piece of metal, which is cold, and then you heat it up in one point, and then you ask yourself, how does that hot spot kind of spread out? Right? And that's actually given, mathematically, it's given by exactly the same equation, which describes the evolution of that probability. And so with that, so since they had, quantitative predictions, so they had sort of like ways of relating all the coefficients that show up in the equation to the microscopic description of water as being made of molecules and so on. It came with sort of quantitative predictions, and the reason why they were important is because at the time, it wasn't actually completely clear that matter is made of molecules and of atoms. Okay, now of course we know that matter is made of atoms, and you can produce microscopes that are sufficiently powerful to basically see individual atoms. But at the time, it was sort of the prevailing hypothesis. So most people believed that matter is made of atoms. But there were sort of competing hypotheses, and there wasn't really a single experiment that had no other explanation, right? And this was the first experiment that really had no other explanation than the fact that water is made up of molecules, right? And so the fact that then Perrin, a few years later, he actually really experimentally verified it, and he figured out that the predictions that Einstein and Smoluchowski made for how far these particles move as a function of their size and the viscosity of water and density of water and so on. But this prediction was actually correct. to within, I don't know, they had like 10% error or something. That really kind of settled the debate about the existence of atoms, right? And actually Perrin then got the Nobel Prize for that in 1926, precisely because it settled the debate on the existence of atoms. And what's interesting is that about the same time, there was a young French guy called Bachelier. And so he was interested in something completely different. So he was interested in what now we would call mathematical finance. Right? So he was interested in understanding the stock market. Okay? And so he wanted to understand how prices, share prices evolve. And, the story that he developed in his thesis was basically the following. He was saying, okay, so you have your share price, and there's lots of people buying and selling these shares. And every time somebody buys a share, that creates a little bit more demand, so it actually drives the price up. And every time somebody wants to sell a share, it kind of, drives the price down. And there are many, many people who do that. In most cases, if you and I, we sell shares for 100 or for 1,000 euros, it doesn't have any effect on, multi-billion-dollar companies. So the individual trades have tiny effects, most of them, but there's many, many of them. And sometimes they drive the price up, sometimes they drive it down. And so there's a cumulative effect, which then makes the price move, but in a sort of, erratic and random way. And so you see the story is basically exactly the same as the one with the Brownian motion, except that now the role of the grain of pollen is played by, the price of the big company, and the role of the water molecules is paid by, the investors who buy the shares and who sell the shares. And in his thesis, he also actually derived the heat equation. So he also said that, so actually the evolution of the prices is described by this heat equation. And now this time it describes the probability that the price takes certain values, right? Rather than the probability that the position takes certain values. And so that was basically, sort of the foundation of modern mathematical finance, and also in particular the works of Black-Scholes, who then got the Nobel Prize for that in economics. Bachelier didn't really get much out of this because he was, in some sense, he arrived too early somehow, and the French probabilists at the time were not particularly impressed by his work, and they also, thought it wasn't terribly great use for mathematics to somehow, describes these lowly material questions of, just prices of companies and things like that. And so he had a really hard time actually finding a job. He had a job at the Sorbonne at some relatively early stage, but then there was World War I, and he lost it. He had to go to fight. And when he came back, the job was gone. And then for most of his life, he was basically giving private math lessons. And he got his permanent job in his late 50s or something like that. So he was a bit unlucky. But then, so you see, the point of these two stories, right, is that you have two situations that are, in principle, completely different. Right? On the one hand, you look at grains of pollen that move around in water. On the other hand, you look at the evolution of stock prices. But then the stories that you tell about them are kind of similar, right? In both cases, there are sort of lots of little things that sort of have an effect, and the cumulative effect sort of makes the large thing move around. That's essentially the same stories in both cases. And by this universality, it somehow tells you that there's actually the same mathematical object behind both of these situations. And so if you want to actually make some real math out of that, right, so you would want, so I already mentioned that there's somehow the heat equation. That is some real math. But that doesn't really tell you how these things look like. What you would really want to do sort of is to somehow say, well, you know, if I look at the trajectory of my stock price, for example, what does it actually look like as a function of time? So mathematically, what this means is that you want to construct something like a random continuous function, which tells you how the stock price moves. And that was actually first done by Wiener. So he was a mathematician at MIT in the 20s. And so it looks like this, right? So actually, I have a movie for that, right? So here, if you want, time is horizontal and the stock price is vertical, if you want. And so here you take, there's this idealized mathematical object, which is now called the Wiener process, which describes this evolution, and that's a random function. And here what I did is I take one sample from that random function, and then I kind of zoom out. It's the same function, and I just zoom out more and more, right? So it moves just because I'm zooming out. And this parabola that you see is just to say that the way I'm zooming out is the way that keeps that parabola fixed. So if I zoom out by a factor 2 horizontally, I actually have to zoom out by square root of 2, kind of vertically, right? So it's like the way of zooming that keeps that parabola fixed rather than keeping a cross fixed, if you want. And if you do that way of zooming out, then it always kind of looks the same. So it has some kind of fractal, self-similar kind of behavior. And then more recently, right, so Donsker, for example, so he really proved a mathematical theorem that in some sense quantifies the statement that, you know, many things that behave in that way, if you look at them on very large scales, they look like this Wiener process, which is this idealized mathematical object that I just showed you, okay? And so now to conclude, I wanted to give you a little bit, right, like all the mathematics that I've been talking about so far, it basically ended in the 50s, or mostly it ended like in the 20s or something. So this was like 100-year-old mathematics. So what I want to do now is give you just a little glimpse into some modern, like, you know, recent mathematics from last 5 years or last 10 years. And so here the situation is, you ask yourself about fluctuations of interface growth models. So here the situation that you should imagine is that there's a two-dimensional surface, and it comes in sort of two types. So for example, here the surface is a forest, and there's a forest fire, okay? And so then there's one half of the surface, which is the bit that was burnt, and then there's the other part, which is the bit that's not yet burned, okay? And there's an interface between the two, which is the flame front. And the flame front, well, here it clearly moves in one direction. It always moves in the not yet burned direction, right? And then what you see, you look at this flame front, and you see that it's, you know, it's more or less like a straight line, but it's not quite straight, right? So it sort of wiggles around a bit here. You know, of course, it's because some bits burn a bit better, some bits burn less well, right? So there are some bits where it moves a bit faster, then it moves a bit slower. And so then you can ask yourself, you know, is there like some kind of idealized mathematical object that describes, you know, the fluctuations of this flame front? But now this time, it's not just a random function of space, it's a random function of space and time, because the front actually moves. So it's like a random movie, if you want. And the same situation shows up in different settings, right? So here, this is a picture from an experiment about liquid crystals. So it's liquid crystals like the liquid crystals you have like in a TV display. And it's a type of liquid crystal that comes in two phases, and they have different optical properties. So on the microscope, you see the difference, right? So there's one type that looks black, the other one that looks gray. And one is a bit more stable than the other. So say the black one is a bit more stable than the gray one. And so what you do is you first prepare it in the gray state. And then what you do is you take a laser beam and you sort of zap the laser beam across it. And when the unstable state gets a bit of energy, it gets activated, it sort of flips into the stable state, right? So basically when you hit it with the laser beam, it turns black. And then the black thing is more stable, so it actually expands, right? So what you actually see is first it's all gray, then you zap it with a laser beam, you see a black line, and then the black line gets thicker and thicker, right? Because the black is more stable. And then this, the edge of the black line is what you see here, right? So it's not quite straight. You see it sort of starts being a bit wiggly like this. And then you ask yourself, how do these wiggles behave? Is there like a natural mathematical model for that? And then you can also come up with just some, random like math models that have a similar feature. So for example, here, this is what I call the Tetris model, right? So the Tetris model is you just have Tetris bricks falling down, right? And so here you just get a big pile of Tetris bricks. So you just imagine the screen is like a Tetris game. So you have the Tetris bricks falling down, they pile up, and you don't play, right? So they just pile up. And so you see something like this, and it's a little bit similar, right? In the sense that now there are two regions that at the bottom is the region that's sort of filled up with Tetris bricks, and at the top there's the region which has no bricks yet. And well, here there's some sort of, it's sort of supposed to be roughly centered at the boundary between the two regions, but here you don't really see much. But if I zoom out, you see better. So if I zoom out, here I see something like this. So now I'm running it much faster, right? So the Tetris bricks kind of fall down super fast. And let me just pause this for a second. Right? So now you really see, right? So there's the region here which is full of bricks, there's the region here which has no bricks, and there's a kind of interface here between the two, which is a bit wiggly like this, and the interface moves, right? Well, now it doesn't move anymore, but it moved. And now you can ask yourself, if I zoom out more and more, do I get some kind of idealized thing, right? So I can zoom out even more, actually, right? And go even faster, right? And you get something like this. So is there like an idealized mathematical model that describes this, just like there is this Wiener process that describes some idealized form of Brownian motion or stock prices, right? So in this case, this is something which has now been described, but this is like work from the last 5 or 6 years or something. So the first actual description of that object was done in 2016, I think, or 15 or something like this. So it's relatively recent. And one can actually describe this object. But for example, the understanding is still by far not as good as what we have for Brownian motion. So in the sense that there are a few toy models. For example, for this Tetris bricks model, there's no theorem at all. I mean, there are sort of very simple theorems, but they basically say nothing about the fluctuations. There are a couple of very, very specific mathematical models that are a little bit similar to this Tetris brick model, for which one can actually show that, if one zooms out in the correct way of zooming out, then there is a limit, and one can actually describe the limit. But the description of the limit is rather complicated. And it's kind of interesting because the description of the limit relates to some completely different area of mathematics, which is called random matrix theory, which in principle has no business showing up, in this situation here. Now, a thing which is much better understood, actually, is situations where fluctuations are symmetric, right? So here, fluctuations were completely asymmetric in the sense that, the Tetris bricks, they only pile up, so they only go up, they never go down, right? The flame front always burns in one direction, it never retreats, right? I mean, once the forest is burned, it's not going to burn again, right? Same for the liquid crystal, actually. It's always the black one that invades the white region, and never the other way around. But there are other situations where you can imagine, two regions competing, and they compete on equal footing, and then, the fluctuations can kind of go both ways. And those are much better understood. And there one actually understands very well what the limiting movie is, if you want. And it has a description which is much more like that of Brownian motion in terms of Gaussian distributions again. And so then one can ask oneself, what if we're in a situation where it's not symmetric, but almost symmetric, right? So say there's two regions, one of them is a tiny bit more stable than the other one. And so it kind of, on average, it tends to invade the other region, but very slowly. And so most of the fluctuations are quite symmetric, but then, it invades a little bit. And then it turns out that, well, if you zoom out by not too far, what you see is basically the same as if it was symmetric. If you zoom out by a lot, then what you see is exactly the same as if it was completely asymmetric. Okay? And there's one, there's what's called a crossover regime, where you somehow move from one situation to the other one, right? And it turns out that that also has some kind of universal behavior. So there's an equation that shows up, which is called the KPZ equation, which I wrote down here, and which is a stochastic partial differential equations. And it's kind of a universal equation that describes that crossover regime, right? And so that by now there's a number of theorems that I've been involved in, which really tell you that there are many situations of that type where that exact same equation actually shows up and describes this kind of crossover regime. And the interesting thing about that equation is that, so I don't want to go over it because basically it's the end of the lecture, but there is this term here which has the square of the slope of the solution. But you've seen sort of from the movie, these things tend to be really quite rough, right? And actually if you do so I have another movie here for the solution of this equation, it kind of looks like this. And in fact, what you see here is that if I freeze this movie, I don't know why the dock here shows up, but so am I able to freeze it? No, I'm not able to freeze it. Anyway, you can kind of imagine what it looks like if it's frozen. If you freeze this movie, right, you see that it kind of looks like one of these Brownian motions, in space, right? And that we saw that it was self-similar with this sort of parabola motion, right? Which means that basically at every point the slope is kind of infinite, right? Because it's sort of tangent to that parabola in terms of zooming out. And it means that, that equation is just complete nonsense, right? Because this here is the square of the slope, but the slope is infinite at every point, right? And so you've got an equation where on the right-hand side there's just a big infinity here. And well, this weird symbol here, that's the noisy bit. That's the thing that makes it random. And that's the thing that makes it very irregular. And so in a way, you have to really write the equation like this with a kind of minus infinity. And then, what does that mean? It's sort of a weird equation, right? And, so there, that's the part that Martina mentioned earlier on, right, is you can ask yourself, do equations like that actually have a meaning, right? And it's not just, right, it's not just an abstract kind of mathematical question, it's really, they show up. I mean, I've shown you the kind of models where they show up. And then you can, really compare. I mean, it's, if you give it a mathematical meaning, is that meaning really the same as the thing that actually shows up, right? And it turns out that you can do that, right? And I think I stop here. Thank you very much for your attention.